Okay, so this question in the stress in beams, at least if you read the first two questions, the A and B, you can see that we need to first calculate the maximum tensile stress, and then the second one is the radius of curvature. So we need at least two formulations that if you remember, or if you want to look your notes, please go to look at the flexural formula that we have. The tensile max is equal negative, or this is m, and then this is y. This is inertia. Okay. Y means the distance from the centroid or from the center of the mass, okay, to the outside of the shape. So in our case, our shape is just a square, I think, right? The beam is square, the cross section of the beam is the square of dimension. So we could take that this beam here, this is a square, so the distance is this half of its this distance, right? So we could take that because of the square dimensions, that y is d/2. This is the stress for tension. And then the inertia is just d with power of 4 divided by 12. Okay? And then what we need to do is we are going to input this inertia inside this sigma max. So we put negative m, and then y is d/2, and then divide by d with power of 4 divided by 12. So we cancel this 6 and this 3. So we get the y also negative, right? Y also negative because let me draw here. Because we are going to take, this is the neutral, right? The neutral axis. So we take that this will be negative d/2. Okay. So we treat the neutral axis as to convert whether it's positive or negative for the signs. Okay. If it's below the neutral axis, it's negative. So we are going to have this negative, so we can cancel the negative sign. So we get the positive. Okay. Remember, in tension, here it's going to be in negative because of the position, okay? Because of the position of the moment. Okay? So the moment here on the below is tension, right? And in the upper is compression. So you need also to think about that compression and tension. Okay, so we could take this and right, this is become 6. And then this will be d cube, and then we just plug in everything inside. So 6 and then 20 kilonewton meter divided by d cube is what? Is millimeter, so I will convert to meter. So 0.12 cube meter cube. So if you check, this will be equal to this will be equal to 69.44 MPa. So this is for A. And for B, the curvature, the formulations for the curvature is you can take m is equal the modulus of elasticity, inertia, and then divide by the rho. Rho is the radius of the curvature. You can see also from the picture here, this is rho, this is, let me write, this is radius of curvature. So So simply we take these formulations and then we are going to determine the rho. So rho will be E multiplied with inertia divided by the moment. Or let me just rewrite inertia directly with the formula d to the power of 4 divided by 12. So 210 GPA. Let me just write GPA first. And then this will be 0.12 meter with power of 4. And then we have 12 and then 20 kilonewton meter. I simply just make some simple calculation here, and then you can just plug in your calculator. This will be equal to 181.4 meter, right? And then we need to also calculate the delta max. Delta max is the deflection, the maximum deflection, this one here. So from the normal distance, we deflect with some delta. And how to measure the delta is basically we are taking the geometric perspective. We are taking the arc as the length. So we take that we know rho, right? We already calculate rho. Let me write here. So for number C, we are going to take, so this is rho. And then this is the some angle theta, right? And this is the beam that deflected, right? And then this is what we are going to find, the delta. The delta max. So assumptions is we are going to take that from this perspective, we could take the theta so this is going to be we are taking, so this distance here above the delta, this is going to be rho, or maybe let me just write with the theta. If we take the angle, this will be the cosine, right? Cosine. Or let me just write. So if this is L, and this L is basically based on the arc, so L will be rho multiplied with the theta. So theta is L over rho. Okay, so this part here is cosine L over rho, right? So basically, the delta, so delta max, I think let me just move a little bit to the left. Okay. Here, that, okay. Okay, so delta max is just taking rho minus this cosine, or, oh, sorry, this is supposed to be rho cosine L over rho. This is going to be rho cosine. So rho cosine L over rho. And then we take this out. And then you simply plug in all the information we are given. The L, the length is 4 meters, right? L is 4 meters, so L is 4 meters. So we could just simply plug in all the informations. 4 over 181.44. So this will be equal to 0.04409 meter, or 44.09 millimeter. Okay. So this is all the answer. Okay. Okay, I think if you are correctly use the formula, and you know what's the question meaning, what's the goal from this question, I think what happened next is just plug in the formula, and plug into the formula, and then just a slight geometric review on the circle, right? On the circle, the curvature. And then you take that beam. So we can, this is our assumption. So we take that the beam are deflected, and then assuming that it is making a circular curvature. And then we can approach with a radius, this rho, and then to find this arc length. And arc length will be, in assumption, the same with the length of the beam. So that's why we are taking this into this equation here. There's a subtraction between those rho and rho cosine theta. Okay, so I think should be if this type of question, you need just to focus on the formula and then find the computations. You can just plug it into your calculator and you get the answers. Okay? And don't forget the units. Okay, I think a few students still forgot how, or maybe not really read the question, so forgot the unit. Okay, so you need to be careful on the unit: meter, millimeter, Pascal, megapascal, gigapascal. Okay. Okay, next question is this. Okay, this is a little bit complex because of the shape. If you look at this shape, here we have not like usual T, we have double T now. So it's beam with the double T here, right? Which means we are going to observe into three shapes. Below, and then this shape here, and then you get all the information. And the picture already given you the neutral axis is around here. Okay? And this is the moment that are applied. So, okay. So determine the maximum moment that can be applied. So we are going to check the flexural formula first. And then we get the idea that it has sigma allowable 200 MPa for the tension, and then sigma allowable for the compression 100. So that is, we are going to take that as our measurement also. So first we need to locate the centroid, the distance. At least we are going to have maybe drawing again to make it easy to see. And then perhaps here. And then another one here. Okay. And then we have this one. This one 25. This one also 25. This one is 50 and 50, so we have side like that, so 50 and 50. And then another 25 here. And then let me make it more proportional. So this is another 25. And this will be 25. And this will be 100. So let's say this is 1. This is 1, 2, 3. Okay. And all of them are rectangular. So we could find each shape, each centroid. Okay. So we take this centroid. The first one is here. Let's name it as C1. The second one here, name it C2. And the third one is here. And according to the picture, we are going to find this, the neutral axis is around in between here, okay, not in the shape, but here. So this will be the total centroid. But let's check all the C1, C2, and C3. Or perhaps let's just find the area for each one. So area 1 is 25 multiplied with 100. This is 2,500 millimeters square. And then this is also equal with A2, so let me just write A1 equal A2. And then A3 is 25 multiplied with 50, 50, 100, 300, right? Or 200. 25. Things should be 100, 50, 50. Oh, 200, 200, not 300. So this will be 5,000. So the distance for the centroid, the total centroid is A1, the distance 1, plus A2, distance 2, plus A3, distance 3. And then divide by total area. So distance 1 is perfectly half of the rectangle. So this will be 50. This is also the same. And for the C3, this will be half of the 25, which is 12.5. So we plug in all. So plug in all information.
I think you could just plug in the numbers, okay? So distance 1 is 50, distance 2 is 50, distance 3 is 12.5 millimeter. Okay, and then plug in the number, divide by total area. You get that the result is going to be 43.75. You can check also. So that is this point here. So this is 43.75. And remember the total distance from the top of the shape until bottom here. This is 100 plus 25, right? So let me write, this is 125 millimeter. So, I'm drawing a little bit longer. So this is wrong here. This is supposed to be not supposed to be until here. Okay. So this is from C to the bottom part. So we are also know from the C to the top, okay? Because we are going to see that between these two sections there will be some differences in the modes. Which one is the compression? Which one is the tension? Right? So we can take 125 minus this 43.75, so we get the other distance. So this distance will be 81.25 millimeter. Okay. So at least we get all the necessary informations. Okay. So the distance will be used for later finding the tension or the compression stress. Okay. And after we get this distance, what's happened next is we are going to calculate the inertia. Okay. Calculate the inertia. Okay, since we have 1 and 2 are identical, so we could take that. So if I write directly the total, let's write inertia Z is twice of inertia 1 or 2 plus, or let me just write 1, okay, and then multiply with the distance squared, and then plus, this will be the inertia 3 plus A3, and then D3 squared. What is D1? What is D3? That is the distance, okay? The distance from the material 1 and distance from material 3. So let me write here. The inertia is, so this is 25 and 100. So remember the inertia for the rectangular is BH cubed over 12, right? So we can write this will be 25 millimeter and then multiply with 100. This is the height, so we take cube and divide by 12. And remember, one thing about this shape, okay? When you are calculating all the distance, all the centroids, etc., do not ever rotate the shape, okay? Because if you rotate, all the assumption will be changed. Do you understand? Because sometimes, for example, if I have this, which one is the base and height? Base is always here, height is here. If you try to maybe switch, maybe you are going to switch this number. Okay? Sometimes that might happen. Sometimes that might happen. Okay, because this is not going to be calculating only the geometric, but we are also considering how it's going to position. The position is important. Okay, this is the inertia, and then plus the area is 2500. Okay, and then multiply with the distance. So this will be 43. So this is 400. How do we know how far? Okay. This is going to be 75, right? Is it correct? Let me check. 43 minus 12. Okay, so that will be. So we need to find this one. We need to find the distance here from the total centroid to the centroid 1. What is that? So it should be it should be 75. Yeah. Correct. So this is 25. So this will be, I think I will rename this as D1. Okay. So then if you read my notes, you know D1 is here. Okay. And D3 is this. I was confused because because the line is a little bit messy. Sorry. So multiply with 75 minus 43.75. Okay, that's the first part, and then plus inertia 3. 3 is 200 millimeter. Multiply the height is 12.5. 25. Sorry, 25. This is cube, and then divide by 12. And then plus area 3 is 5,000, and then the D3 is 43.75 minus what? 12.5, right? This one D3. So 43.75 minus this. So D3. So this one, there's this formula. You see D is the distance from the centroid, the total centroid to each centroid. So for example, this is 3, it means the distance from centroid to the centroid 3, each shape. And since our shape for 1 and 2, they are basically the same area, the same distance, so we just multiply by 2 in the front. Okay. That's why we have just here. But if you have like different criteria, so we need to plus within three formulations. Okay, so we take that and then it's squared like that. Okay, and then we take the calculator. This will be quite big number, I believe, because it's in millimeters, so it will be I think million. So for this, I will just write the approximations. So 14, 19, 27, multiply with 10 with power of 6, millimeter with power of 4. So at least we are halfway. Okay, so the question is actually asking the maximum moment. Okay, the moment that we need to apply. Okay. If we have this sigma, this 2 sigma allowable. So let's use the sigma allowable as our computations. So let me write here. The sigma is negative m z y I z. So which one compression, which one tension? You see the moment is going to be here. So we are going that. Okay. So which one? The top or the bottom? For the tension. Top, okay. So the bottom will be compression, right? So we are going to use this distance, each one within each tension or compression. Okay. And then I think we could assume, I think I mentioned that we can maybe make default for the signs. For example, this one here, like that, the M, we can assume that this will be negative, and if this is like that, this is positive. Okay? Just to help out in the computations. Okay? But if you really understand, that doesn't really really matter. Okay? Okay, so this part here, that the M will be negative M. So M, we are going to take that and divide by Y. Okay. So first we can take the, I think we can take this a little bit to the left. Here also going to the left. And the picture also to the left. Okay. So we can take, for example, the tension. So tension. So we are going to take M max and then write T for tension. So equal. This will be, tension is 200, right? 200, and then Newton over millimeter squared, the MPa. Multiply the inertia is 14.1927 million. So multiply with and then divide Y. Y will be 81, right? 81.25. Okay. And you will get some number here, which give you this approximation around. And it doesn't really specify which conversion unit that you need to use. So I believe the results would be within all conversions still be okay. So Newton meter okay, kilonewton meter or kilonewton millimeter, that's fine. So this is the tension, and then let me write here M max for compression is 100. So 100 multiply the inertia and then divide with. Now we are going to have negative 43.75 because it's below the neutral axis. Oh, this is also negative, sorry. Because this is a compression, so this is also negative. And then this will be equal 32.44. So we have two different moment here. Okay? Two different moment. But which one would you take? Which one? That you need to allow the design. Okay? Which M? 32 or 34? It is basically what? 32, right? Right? Okay. Any others? Do you understand why we pick 32? That's correct. Correct answer. But why we need to pick 32? Okay, so in design, we get two allowable, right? We get the compression, we get the tension. And then from two different approach, we get these two different numbers, right? The safest one is if we apply directly 34, it seems that if we are going to look at the allowable at the compression, or is allowable in the tension, perhaps it's safe, right? But if we look at the compression, it's not safe if we take more than 32. So the safest one is we can say that, okay, this can be applied to this 32. If more than that, we'll be very trouble. Like you are going inside the elevator, you have the maximum, right? Like how many kg in the elevator. Of course that you are not, if you are like maybe over capacity, there will be some alarm, right? You need to get out. So they are also applying the allowable weight, right? Or allowable stress inside. If there is maybe increasing higher than the yield, right? The yield stress or yield strength, then it will be destruction. So we are going to take this. Okay? So the maximum M that we are going to take kilonewton meter. So, yeah. Because this is, again, the maximum doesn't really define it is the highest one. No, this is the safest, the max, the safest in comparison. Okay, and another side from the design is perhaps besides we find how much a moment or how much the tensile or compression that we are going to apply, we can also perhaps calculate the shape, okay, which one that is going to be required. Okay. And sometimes for beams, we have some criteria that has been, we say, standardized. Okay. So if I take you to the, for example here, this is property for the steel or wide flange shape, which means that this is going to be like this. Okay. Or we can see another shape like this, or perhaps here like that. Okay, and then it has two different units, the US and then the SI units, and we have this also. Okay, so and all of this, they are all standardized. So for example, we have this designation. Okay, it means that this is the code. So for W69027, you have the area, you have the depth, you have the width, and the thickness, all the things that are standardized. So if, for example, this type of question is appear in your exam, I will also provide this, and I hope you can familiarize with the property. I also prepare some of the exercise for this chapter, and then apply this table, and then you can just find which one is the suitable one for each question. And then you have also this elastic property. Okay. And what else do we have here? Okay, the plastic modulus also we have. Okay, and so this is dimension, this is the elasticity. All right. I think that's all for today's class. And I think I mentioned early in the class. So I think next week we don't really need to have a class. Okay. So you can concentrate to other course. I will provide some additional content for maybe the solution or some practices that I think important, but I think not all exercise, but I will pick which one that has importance, and I will have a video solutions and will be uploaded